We're on to chapter 7, which is all about optimization. So we will be using the techniques that we've developed for finding local and global extrema in order to apply those in situations within the context. There will be some simple optimization problems concerning mostly various shapes, as well as realistic biological problems requiring a bit more interpretation at the end. Let's start with just thinking about what is an optimization. What does it mean to optimize something? To optimize means to find whatever is best. Best will depend on the context, and generally there are a series of steps that one should follow in order to really be able to set up the problem mathematically and then tackle it. First of all, because the problems will be word problems, we will need to identify all given quantities and assign variables to them. The thing that helps a lot here is in fact to sketch a picture where possible. Just like before, the graph is useful not in just visualizing things, but often in determining what are the important quantities. The second step here would be to construct the objective function. Objective function, that's what we call the thing that we're actually trying to maximize or minimize, whatever it is, what you're trying to optimize. After you've done that, oftentimes your function will have more than one variable in it, and we'll see an example in just a little bit. So what you have to do is figure out potentially other relationship between your variables, so your optimization objective function only has one independent variable in it. Once you have all of that down, so once you have a function that depends only on one variable, then it's just calculus techniques that we've discussed in chapter 6. So let's take a look at the very first, simplest optimization problem. I titled it, which rectangles are best? Again, it really depends on what your definition of best is. And in this first slide, I am looking to find rectangle of a fixed perimeter, 100 meters, let's say, with maximal possible area. This really is a fairly realistic problem. Let's say you have a fixed amount of fence and you're trying to enclose as much land as possible. My friend Paul, for example, actually did have to apply calculus to build a coop for his chickens, and we always think that it's such a stereotypical mathematical problem, but it actually happened to somebody I know in real life. So first step is to draw a picture, because once again, it will actually allow you probably to figure out what the necessary quantities are. So I'm after rectangles. So let me draw a little rectangle. And I know that it has to have perimeter of 100. So I need to know something about the total amount of side lengths here. What I'm trying to maximize here is all the area that it encloses. So what are some of the variables that will describe my rectangle here? Clearly, length and width are good things to assign to it. So let's say, well, I guess if anything, this is length and this is width, okay? And so then let's write out what is it that we're actually trying to optimize. That's when you look for words like maximum or minimum, or what is it that is important to you in this problem to make as small or as big as possible. So the objective function here will be the area function. The area of a rectangle is length times width. And here is where we see the first problem. Just like discussed on the last slide, our objective function is the function that we will then like to take a derivative of, find critical point, and find eventually local and global maximum. But the problem here is it has two variables. I don't know how to take derivatives of a function with more than one variable, okay? So we have to get rid of one of those variables, and we're going to use what we call a secondary equation for that purpose. Secondary equation will be an equation that somehow presents another relationship between my two variables here. So there is still a piece of information in this problem I have not used, and that is the fact that the entire rectangle has to have perimeter of 100. So perimeter is all the way around, which means that 2w plus 2l is what composes 100. I'm now going to solve this equation for one of the variables and then use that to replace that variable in my objective function with. Generally, there might be some considerations as to what variable is better or easier to solve for. This equation is very symmetric for L and W, so it really doesn't matter. Let me solve it, for example, for L. So I'm going to divide everything by 2, first of all. And then from here, L is equal to 50 minus W. So I can use this to plug in for L in my objective function, which will result then in my area being 50 minus W times W. Or if I want to open up the bracket, 50W minus W squared. And this is the function that I'm going to want to maximize. Okay? After this, it's the standard calculus tools from the previous chapter. So what we're going to do here is take the derivative of the function, find the critical points, and then analyze those. So in order for me to find critical points, let's first find the derivative. In this case, it's fairly straightforward, 50 minus 2W. So critical points, I need to set the derivative to be 0. And I need to consider when the derivative does not exist. So in the first case, the derivative is 0 at 25. And it does not exist nowhere because it's a nice polynomial function, so I have no solutions there. So I only have one critical point. And now there is a number of ways to proceed. You can use the first derivative test or the second derivative test. You can also find endpoints and plug those in. This is completely up to you. And in fact, every problem will probably have one of the methods being the quickest or more efficient, but there's also methods that you will be more comfortable with. So from here on, you can find endpoints, you can use the first derivative test or the second derivative test in order to actually find your global maximum, okay? So figure out which way you would like to proceed. For those who would like to think about endpoints, in this case, we're not given the actual exact interval. We have to figure it out ourselves, which is probably why some people don't like the endpoints method. You would then have to think about your variable here, which is W. What is the smallest and the largest that W can be given a constraint that all the way around your perimeter still has to be 100 and that you're trying to maximize the area, right? So the simplest thing I can say about W here is that it has to be greater than 0, but that doesn't give me the biggest value that the W can be, okay? So what I strongly recommend here is to actually apply either one of these methods to find the maximum of this function, the global maximum of this function, okay? Feel free to try all three of them. I think this will be a wonderful exercise. It does turn out to be that this critical point is the global maximum. Our conclusion is that the rectangle with the largest possible area has width 25. What is its length? Well, all the way around was supposed to be 100, right? And so I can also even use this equation to solve for L. So if W is 25, 50 minus 25, it will turn out that L is 25 too. So the best rectangle is a square. Now, of course, that depends on your definition of best. In our case, it is the most area for the least amount of perimeter. So out of all the quadrilaterals, which means shapes with 4 straight sides, square will have the most area enclosed in it. And that's true in general. These kinds of problems have an inherited symmetry. The shape that is most symmetric will have the most area in it. So out of all the triangles, an equilateral one will contain the most area, and so on. So the polygons, so shapes with straight sides that have all equal sides, are called regular polygons. Now, what if I'm not constrained to using 4 sides? So what if I have fixed amount of perimeter, but I can use as many sides as I want? Which one of these shapes will now have the most area enclosed within it? Is it a triangle? Is it a square? A pentagon? A hexagon? It doesn't take very long to persuade yourself that the more sides, the better. So in fact, something much closer to a circle will include the most amount of area for the same perimeter, okay? Now, a circle, of course, is not a polygon, but if you have lots and lots of sides, that's a pretty good approximation of a circle. So circles are great for a number of reasons, but they're terrible for one particular reason. What if I don't want to just build one pasture to enclose my animals in? What if I want to build a few? Circles, while they are the most efficient in terms of area for the perimeter, are terrible at packing, right? So if I did have a bunch of circles, you'll notice that I'm actually wasting quite a bit of space because there is going to be inevitably space between them that I'm not covering. So I'm losing out my field area by having these gaps between the circles. That's why polygons, so things with straight sides, are good, because straight sides can go against straight sides and guarantee that I don't actually lose any shapes. Now, this actually gets to the bottom of a really deep mathematical result that was only proven a few years ago, that there are only 3 shapes that what we call tile plane without gaps. So out of all of these regular polygons, there's only 3 that I can pack together tightly without producing any gaps whatsoever. And the shapes are the triangle, the square, and the hexagon. Now remember, what we've discussed just now is that in this lineup, the more sides, the better, because the more sides guarantees larger area enclosure for the same amount of perimeter material. So out of all of these 3 shapes, the one with the most sides is, of course, a hexagon. So this is the most efficient tiling for the least amount of work in producing of the actual sides. Now stare for a minute at this tiling. What does this remind you of? Where do we see this in nature or otherwise? To me, this looks like one very particular thing, and that's a honeycomb. And in fact, the mathematical result I've just mentioned is called the honeycomb theorem. This is the most efficient tiling, and that is the reason why bees use it. It uses the least amount of material to produce the most amount of area, and it doesn't waste any space in between their little cells. So the conclusion is bees know math.
Let's take a look at a real-life application next. So on the picture here, you see 2 different types of milk jugs. I have a small child, so we buy lots of milk. And in Canada, in BC, it actually looks like this. So this is the standard BC jug of milk shape that you will see in the store if you want to purchase 4 liters of milk. However, whenever we go camping in Washington State in the US, we see these types of milk containers. You notice the quite different shape. The US jugs are taller and skinnier. So this is what we see in US jugs. Now, I can't guarantee that this is what the US jug looks like across the entire US, and I am certain that this is not what the Canadian one looks like across Canada. So take this and maybe do a little bit more research on that. But the problem here is, when I first noticed, I thought, well, I wonder why the American looks different from the Canadian one. And I actually discovered that Washington State switched over to this shape of the jug about 7 years ago. So they used to have jugs just like the Canadian ones, and now they introduced the new shape. If you want to pause the video for a second and think about this, what do you think is better about this shape that the Washington State specifically switched from the Canadian looking jug to this one? Well, one big advantage is actually the flat top of these jugs, which allows them to be stacked one layer on top of another layer on top of another layer. The way that they store them now is actually stack them up and then shrink wrap the whole thing around. The purpose of that was to reduce costs by getting rid of the milk crates, which have to house these types of jugs because they're not stackable due to their top shape. Because apparently the milk crates used to get stolen all the time, a problem I did not realize was an actual issue. And also they had to be constantly washed and sanitized because this is dealing with dairy. So in order to reduce cost, it was thought that the stackable containers would be better. Ironically, though, it turned out a year later or so that shrink wrap that these guys are then coated with actually cost so much and is so bad for the environment that the industry has been reconsidering going back to the previous shape of the jugs in the first place. So this is another example of just because you can see one particular benefit to something, for example, the flat tops of it, doesn't mean that you should not consider the rest of the setup. Our question here, though, is which shape is better in terms of economy? So industry prefers jugs with these types of shapes because of their stackable abilities and the ease of being easily packed into crates. But what about the amount of material used per volume? So what we would like to figure out is how to minimize materials needed given the actual fixed volume for the jug. Minimize materials needed. So this really refers to surface area because that is how much plastic will go into producing a milk jug with fixed volume. Now, the units are, of course, not exactly the same because in Canada we use liters and in US they use gallons. So let's fix the volume at some specific number that is close enough to both. So we will say 1.4 liters. This will allow for a little bit of room on top of the Canadian jug and a little bit more room on top of the American one. This is close enough to the 1 gallon that we will simply make this assumption. Now, we are going to try to model the actual shapes of the jugs. However, as you noticed on the previous slide here, these shapes are pretty complex. In particular, they involve handles. So we're going to make some simplifying assumptions about the shapes overall. We're going to think of them as rectangular prisms. Okay, so we will think like maybe if I fold this over into the actual handle, then the entire shape can be thought of as a nice tall rectangular prism here, right? The one thing that we will notice too is that because the crates or shrink wrap or something like that have to be packaged onto trucks, the industry does stick to square bottoms of the jar, no matter what the rest of the shape actually looks like. So our overall shape, we will then assume is a square bottom and a tall rectangular, or however tall it is, a rectangular side. Okay, so in the Canadian jug, we can notice that this shape is generally much more cube-like, and in the American jugs, we notice that it's a lot more elongated height-wise. Okay, so we're going to assume that the bottom is a square, which again makes it good for packing. Think about 2 slides back talking about the tilings of the plane and the fact that squares will, of course, tile a plane. And the height is some other number. Okay, so our assumptions here: square bottom and rectangular prism shape. That's what the overall shape is actually called here. So let's go back to our objective function and our constraint. The thing that we would like to, in fact, minimize is the surface area. So our objective function will be the function for the surface area of this entire jug. So what is my surface area here? I have this shape and everywhere has to be covered in plastic. So I noticed that all the lateral sides are all the same shape. And in fact, they are the shape of a rectangle whose sides are X and H. And there is, of course, 4 of them. So overall, my surface area will be the 4 lateral sides, all of the area X times H. So let me label this sides, lateral sides. And the other parts are the top and the bottom. And we of course notice that by our assumption they're square, so they will both be x squared in area, and there's two of them. Okay, so this is top and bottom. Now we see the exact same problem we saw before. The function that we're trying to minimize, the surface area, in this case has two variables, x and h. And in order for us to apply calculus tools, we need to apply them only to one. We need to have only one variable to actually apply the derivative and then figure out the critical points and so on and so forth. So this is where a secondary equation will come in. So what information have we not used yet? Well, we know that we want to minimize the surface area, and this is our objective function, but the information we haven't used yet is that our jugs is supposed to be of a fixed volume of 4.1 liters. So what is the volume of this shape? Well, the volume is the product of all three dimensions. So x times h. So x squared times h. And I know I would like it to be 4 liters. Now each liter is 100 cubic centimeters. So altogether, this will be 4,100 cubic centimeters. You can of course pick another unit of measure like decimeters or something like that, but centimeter seems to be the most reasonable. So now the next step is I'm going to use this equation to solve for either x or h so that I can replace it in my objective function and end up with a function of only one variable. Now here we actually have a choice. Do we solve for x or do we solve for h? Notice that if we decide to solve for x, it's present in the square form, so solving for x will be more difficult. And therefore, the simpler solution seems to be to solve for h. So h from here would be 4,100 divided by x squared. And then I'm going to plug this in for h in my objective function. Now, just because I said that solving for x will be more difficult doesn't mean that it's not a valid approach. You can of course solve this equation for x and then replace x in both places here and end up with the surface area only in terms of h. That is totally valid as well. However, this will likely take more time to then work with as a function. Okay, so what do I have here? I have 4 times x times h, but now my h is replaced by this expression. So 4,100 divided by x squared plus 2x squared. Okay, and let's simplify this a little bit. I notice that one of my x's can get canceled here, and I can put together the two factors. So altogether, I will end up with 16,400 over x plus 2x squared. And one important constraint is the fact that x here, because that's my variable and that's the one that I'm going to be working with, is actually greater than 0, because x measures the width of the actual base of my container, so it has to be positive, and x cannot be equal to 0 because it's present on the bottom here. So now I have this function as a surface area, and that is the thing that I would like to minimize. That is now all the context that I have to think about. What is coming up is simply calculus. I am minimizing this function for x greater than 0. So pause the video here and actually go through the calculus tools that we have learned in order to find the minimum of this function for x greater or equal than 0 to figure out what the shape of the jug is going to be. So back to the solution. Here's our function. There are only so many ways that we can proceed from here. We know that we need to minimize it, so we need to find the actual derivative of the function first. So what is it going to be? It's going to be 4x plus the derivative of this. Now this is something that you might want to do maybe a little bit on the side. This is actually 16,400 times x to the negative 1, and then we can apply the power rule. So negative 1 comes down, and we will end up with 16,400 divided by x squared as the actual derivative here. Now, because I'm going to analyze this using critical points, so thinking about where derivative is equal to 0 and does not exist, it will be easier if my derivative is one big fraction. So I'm going to do common denominators between the two pieces. So I'm going to end up with 4x cubed minus 16,400 divided by x squared, and that is my derivative. So what about critical points? I need to think about where the derivative is 0 and when the derivative does not exist. So this will give me my two cases for the critical points. Because now my derivative is one big fraction, it's equal to 0 when the top is 0. So notice that again, I can only do this kind of analysis when it's one big fraction. I cannot do it on the two separate pieces here. And the derivative does not exist when the bottom is equal to 0. So this will produce two separate things for me. The top is 0. I have 4x cubed minus 16,400 is equal to 0, which will give me one solution of x approximately equal to 16. And the bottom being 0, of course, produces x equals 0. But notice that I need my x to be strictly greater than 0. So this solution is not in the domain, which means that I only end up with one critical point, namely x being approximately equal to 16. So the only critical point is x equals to 16. I'm going to say equals at this point now. I've decided that this approximation is good enough as a solution to this equation once you take cube roots, so I'm just going to stick to 16. So now there's a couple of ways that you can go. You can apply the first derivative test. You can apply the second derivative test by taking the second derivative. There are a number of ways you can do. I am going to apply the first derivative test, and I encourage you to actually calculate the second derivative of this and apply the second derivative as extra practice. So I am going to use the first derivative test, which means that I need to draw myself a number line, put all the critical points on it, well, there's only one, 16, and then decide on what the sign of the derivative is and what the corresponding behavior of the function is. So if I pick a number less than 16, for example 0, and plug it into my, well, 0 is not good enough, it's not in the domain, so bad, Ksenia. Let's pick number 1 and put it into our derivative here. If I plug it into the derivative here, the derivative will be negative, which means the function is decreasing. And if I plug a number bigger than 16, like a million, I can notice that if I plug in a very large number, the top is going to be positive, the bottom is always positive, so the overall derivative is positive, which means the function is increasing. So that, by the first derivative test, means the function is decreasing, then it's increasing. So at 16, at this critical point down here, we have ourselves a local minimum. Now, this is not good enough yet as the final answer to our problem, because this gives us a local minimum. I don't need to know for which point the surface area is a little bit less than for the others. I need to know the number at which I have the global minimum for this problem. So I need to somehow figure out whether this local minimum is or is not a global minimum as well. So that requires me looking around at the behavior of the function around 16. As we've already discussed, this is my only critical point, and I noticed that the derivative is negative for all the values up until 16. So the derivative is negative for all x less than 16 that are in the domain, so all x's that I care about. And I noticed that the derivative is positive for all x greater than 16. So up until 16, the function is always decreasing. And after 16, the function is always increasing. So there's no way that I can ever fall below this local minimum, right? It cannot decrease afterwards because that goes exactly against the actual behavior of the function. I decrease to this point and then I increase forever after this point. There's no other critical point here that can turn the function around and change its behavior. This is the only critical point for the entire function ever. So that means I will decrease to this value and I will always increase after, making this also a global minimum. So therefore, this means that x equals 16 is also a global minimum. Now, I want to pause here for a minute and go over this again. Just finding out using the first derivative test that a critical point in your problem is a local minimum is not good enough. You need to justify that it's also a global minimum, because that is what the actual problem is all about, finding global extreme. So if this is the global minimum that we were looking for, it means it occurs at x equals 16. We were asked for the problem, which shape of the milk jug is the best? So now I have that x is approximately 16, but I still don't know the value for h. So I know that my jug has to be 16 by 16 on the bottom, but I don't know how tall it has to be. Remember that secondary equation actually gives me a relationship between x and h. So if I just plug in x equals 16 here, I'll be able to figure out the value for h. So h is 4100 divided by 16 squared. And if we go through that, we will notice that h also comes out being 16. So that means that the best shape in terms of smallest surface area and the fixed volume for the milk jugs is in fact a cube, 16 by 16 by 16. The optimal shape is the cube. So this is not terribly surprising. Think about the previous question. We were wanting to figure out what is the optimal rectangle with the smallest perimeter and the largest area, and it turned out to be a square. The best rectangular prism with the smallest surface area and fixed volume is the cube. The most regular uniform shapes are actually the most optimal in terms of enclosing the fixed volume within the minimum surface area. Now, what does this mean for the jugs? Well, thinking back to the picture, the Canadian jug is most certainly closer to the cube shape than the American one. So if we actually calculate the volumes based on approximate measurements of the jugs themselves, we will notice that, of course, the US shape has a smaller base and a higher volume, which results in a surface area of approximately 1580. The Canadian size has a larger base than the US and isn't as tall, which results in being closer to the cube and therefore smaller surface area. The optimal size, which will be the cube, which again is closer to the Canadian than the US, will result in an even smaller surface area, and this is the smallest possible surface area that will enclose this amount of actual volume. So, despite the fact that Canadian is closer to the optimal, it's not quite there yet. The best milk jugs would be literal, perfect cubic ones. Now, as I mentioned, the actual milk jugs differ in shape even across the provinces. So the one thing, for example, that Ontario has going for it is they actually sell milk in bags. That certainly optimizes the surface area and minimizes the amount of hard plastic used. This next example is a fairly standard optimization problem, and I'm going to leave it up to you to actually set it up. So make sure you go through, set up the objective function, set up the secondary equation, and then apply calculus techniques to actually find the global maximum or minimum, depending on what it is that you're actually looking for here. I'm going to go through the examples for the cell application that we have seen at the very beginning of the course. The question here, though, is not about what cell sizes are depending on how they consume and absorb nutrients. It is a further question about the net rate of increase of nutrients and when is that the largest for the cells. So let us remember from the very beginning of the course that the cell absorption is proportional to the surface area, which means that the absorption is some proportionality constant times the surface area of the cell. Now here is where it's important to realize that our assumption is that we're working with spherical cells, so the surface area of a sphere of radius r is 4 pi r squared. Consumption is going to be proportional to the volume of the cell, and again, in our case, it being the sphere, it's going to be 4/3 pi r cubed. Now, for the proportionality constants, we always have that they are positive. And in this case, too, of course, r corresponds to the radius of the cell, so it has to be non-trivial and positive. Now, the question here talks about the net rate of increase of nutrients. The net rate is how much the cell absorbs minus how much it has to consume in order to actually sustain life. So the net rate, which in this case is denoted by N, is going to be absorption minus consumption, or K1 times 4 pi r squared minus K2 times 4/3 pi r cubed. And this is what we are trying to minimize or maximize. We're trying to optimize. So now let's see what the question actually says. Find the net rate the largest. So in this case, we would like to maximize this for r being greater than 0. Now, I can of course include the trivial cell here just because there are no denominators, so I'm not mathematically prohibited by having the cell of 0 radius. Notice here that this problem is a little bit different from the ones before because I actually only have one variable, and that is r, and so I can get to my calculations immediately. I don't need to set up a secondary equation or anything like that. I can start maximizing right away. So the first thing I'm going to do is find the derivative of my function and compute the critical points. So remembering that pi is a constant, k1 and k2 are constants, and my only actual variable is r, my derivative here is going to be, let me write them in order. So k1 times 4 pi, these are all of the constants within the first term, times the derivative of r squared, so 2r, minus, now I'm going to do the same here. I'm going to rewrite all of the constants first. So k2 times 4/3 pi, and then the derivative of r cubed, which is 3r squared. Okay, now let's clean this up a little bit by combining constants and whatnot. I'm going to have 8k1 pi r minus 4k2 pi r squared. Excellent, this is now my derivative. The next step is to find critical points. Remember that the critical points is when the derivative is 0 and when the derivative does not exist. So let's take a look at what happens when the derivative here is 0. So I have 8k1 pi r minus 4k2 pi r squared needs to be 0. Remember that what I'm trying to do here is factor, not divide. So what are the kinds of things that these two terms have in common that I can factor out? I can see that I can take out 4, I can take out pi, and I can take out one of the r's. So overall, I can take out 4 pi r. What am I going to have left is going to be 2k1 minus k2r. Excellent. Now that I have this equation in two pieces, I know that the product of two things is 0 only if one of the things is 0. So either 4 pi r is 0, which means r is 0, because surely 4 is not 0 and pi is not 0. We know their values. Or this second bracket is 0. And if I set this to be 0 and solve for r, my only unknown, remember that k1 and k2 are constants, I'm going to get the value that r is equal to 2k1 divided by k2. So these are my two critical points from the case of the derivative being 0. What about the derivative not existing? Well, let's take a look at the derivative. This is my derivative. There's no denominators, no square roots, nothing scary like that. So this will produce no solutions. Okay, so that means that my only critical points are these two, 0 and 2k1 divided by k2. Now, after this, again, there's a number of ways to proceed. You can do the first derivative test or you can do the second derivative test. Let's use the second derivative test just to change things up a little bit. So for the second derivative test, what we are doing is taking the second derivative, and then once we have computed that, we will be plugging in the critical points into the actual second derivative. Notice that I don't have to really worry about this critical point being 0 here because I'm trying to maximize for all R values above it. I realize that when R is equal to 0, my entire net rate is going to be, in fact, 0, which is almost certainly not the maximum. So let's take a look at the second derivative. This is my first derivative here. Computing the second derivative should be fairly straightforward. I'm going to get 8k1 pi minus 8k2 pi r. Okay? And so let me actually factor things out just so that it's easier to see what the shape of the thing is. I can take out 8 pi, and what I'm going to have left is k1 minus k2r. This is my derivative. In order to apply the second derivative test, I'm going to take my critical points. Again, I don't so much really care about r equals 0. I'm going to take my only non-zero critical point and plug it in. So 2k1 divided by k2 goes in for r. So that means that this r has to be replaced by this expression. Okay, so what am I going to have? I don't want to write out all of the math. Let's take a look at this quickly. So I'm going to have k1 minus k2 times 2k1 over k2. Notice that k2s will cancel out, and I'm going to have k1 minus 2k1. 1 apple minus 2 apples is minus an apple. So this entire bracket will become minus k1. And then I have to multiply it by 8 pi. If this was a little too quick for you, please be sure to actually go through these calculations by hand yourself. But here's what we're going to end up with in terms of the second derivative computed at this critical point. Now remember that k1 is positive. Pi is, of course, also positive, and so is 8, which means that this entire expression is going to be negative. And that is what is important for the actual second derivative test. If the second derivative at the critical point is negative, it means that my critical point, so r equals 2k1 over k2, is actually a local maximum. Let's recall the actual intuition behind it. What I have is a critical point, which means, and it actually is a critical point that comes from the fact that the derivative was 0. The second derivative at that point is negative. The second derivative corresponds to concavity. So that means that at that point, the function is concave down, because the second derivative is negative. The function is concave down, but the first derivative is positive, which means that it has to be the point on top of this little hill, which makes it a local maximum. That is how the second derivative test actually works. Now, the other thing that we have to notice, this isn't yet a global maximum. We have to justify the fact that it is, but it's the only critical point really in our domain of interest. So that means I can say, since it's the only non-zero critical point, it also means it's a global maximum and the only one, so it's the global max. Okay? That means that the thing that we're trying to maximize, the net rate of increase of nutrients, is greatest for the cells of this radius. Okay, so we actually found that the radius for which it's the greatest is equal to 2 times the proportionality constant that was applied to the absorption divided by the proportionality constant that helped us put together the consumption. This is the radius of the cell when the rate of increase of the difference between the absorption and consumption is actually the biggest. Think about this number and also think about the point of equilibrium that we derived early on in the course between the absorption and consumption. How do the two values interact? That rate that determines how big a cell can be, and this rate that determines what is the best in terms of the difference between absorption and consumption. Take a look at the two values, maybe draw a couple of graphs, and think about how that relates to the biology of the cells.